So let's clean this derivative up so that we have an easier time setting it equal to our slope. So I'm looking at this here. Maybe I can push things together. The negatives can cancel out. I can put the numerator 5. I can put the denominators together. The 2 and the square root can, or the negative exponent can come down to the bottom. All right, so this is my other portion that I need. So now I have the 2 parts that are required for mean value theorem, the slope formula, and the slope. All right, any questions? So we'll set these 2 pieces equal to each other. And now what we have left is just an algebraic problem, right? We're going to cross multiply and just try to figure out a way to solve for x. We get the 2's to cancel out. I can divide the root 10 over. My goal is to solve for x. I'm going to get this parentheses by itself first, then I can deal with the 1/2, and then I can get inside the parentheses, and then I can solve for x. So if I divide both sides by root 10, okay. So we have the parentheses isolated. Now we want to get inside the parentheses, but what can we do to handle that 1/2 there? Yeah, let's square both sides, right? That way we can clear that left side without the exponent and then balance it on the other side. Square both the numerator and denominator. I can cross multiply further, but maybe I can reduce this fraction here. This is 5/2. Okay, if I put this over 1, it makes it easier to see. Okay, if I just cross multiply, I can solve for x without having to deal with the fraction anymore. Okay, divide both sides by 10. So what we have achieved here is we found the location on the graph where there's a slope of root 10/2. And this location is guaranteed to be sitting between the endpoints. Let's double check. Yes, right, falls nicely somewhere between 3 and 5. So our C value is 4.5. Okay, any questions about procedure, about the steps? Yeah. Oh, from here? Got it. So when I cross multiply here, I did 2 times 25 minus 5x, and I set it equal to 5 times 1. So I multiply those two together, and I multiply those two together. And then just distribute it through. Divide both sides by 10, and I got that 4.5. Okay. Good. Any other questions with mean value theorem? Okay, let's go to the back page. 6 and 7, I had that as homework, but I'm not going to go through the problems in detail, but I am still going to kind of talk through the steps to make sure that we understand the steps at least. In terms of, but I think it's easier, right? I think those, I don't foresee students having as many issues with first derivative test and sign lines for concavity. So number 6 says find relative max, relative min using the first derivative test. So we find f prime, we set f prime equal to 0. We factor the 3 out, we solve for x, we get 9 and negative 1. We place those critical numbers onto our slope sign line, and then we test values in each interval. And then when we test values in each interval into the derivative factored form, all we care about is it positive or negative? If it's positive, we know that our graph is going to be rising in that interval. If it's negative, we know the graph is going to be falling. And then we can begin making our statements, right? Relative maximum, when we see a sign change from positive to negative. Relative minimum, if we see a sign change from negative to positive. If I want to write increase statements, it would be increasing in the first and the third interval because f prime is greater than 0. Decreasing in the second interval from negative 1 to 9 because f prime is less than 0. I think typically I don't see students having trouble with 6. I think the only thing that I see with problems like 6 is students forget to write because statements. So you got to write because statements for increase, for decrease, for relative max, relative min. A lot of students tend to leave out the because statements for max and mins. So just be aware of that. Okay. Any questions about the process for number 6? Okay. For number 7, it says find intervals of concave up, concave down, and points of inflection. So basically, imagine you're just doing everything that you did with first derivative tests, but you're doing everything from a second derivative function. So instead of setting f prime equal to 0, you're setting f double prime equal to 0. And then instead of you're putting your critical point onto your first derivative sign line, you're putting onto the second derivative sign line. Negative and positives no longer represents positive and negative slope. Now they represent curvature. They represent concave up and concave down. Your critical point is no longer a candidate for max and mins. Now these are candidates for points of inflection if there's a change in sign. And then you're going to write because statements like how you did with the first derivative test. For point of inflection, you don't have to specify the changes from positive to negative or from negative to positive. If you just say that f double prime changes signs, that is sufficient. But for max and mins, you do have to specify which comes first, followed by which sign. Okay. Any questions with 6 or 7?
When you're writing the point of inflection, can you put like f of negative 1/3 for the logo?
Yeah, that's fine. I think for now, I'll probably just have you guys just indicate the x value for me. But eventually we're going to have to finish chapter 3 where we have to sketch out the physical points, and we may have to find those physical points so we can actually put it onto the graph. So, but I do want to just make sure that we understand that if we were to find the physical points on the graph, like max, mins, and point inflection, these x values would go where? Where will we find our order pairs? Into f prime, into f double prime, or into the original function? Original, yeah. Original is how I got that 7.074. If I want to find the physical order pairs for max and mins, they would also go into the original function. But on the quiz, I'll probably just ask you to give me the x values. Okay. I do want to step through number 8 with you because that's kind of a new topic that we just talked about yesterday. Kind of gives us a chance to get some more additional practice in. So let's look at number 8. This is finding max and mins, but using the second derivative test. Okay, so number 8, use the second derivative test to find relative extrema. We want to find max and mins. Let me recap the steps for a moment here. So second derivative test, remember, we find critical points from f prime. From f prime, we set equal to 0, we find those critical points. But rather than creating a sign line from f prime, we're going to take these critical points and we're going to put it into the second derivative function. Okay? And then from there, we look to see if it's positive or negative. If it's positive, we know it's concave up. If it's concave up, we know that the graph must have a relative minimum there. Okay? If we plug into the second derivative and we get a negative value, we know that negative value is going to correspond with concave down. If it's concave down, the graph looks like this. So the graph looks like this. That critical point must be a relative max. Okay, so ultimately, in a nutshell, for number 8, second derivative test, we set f prime equal to 0, and then we take those critical points and we put it into the second derivative function. So that's basically the steps for second derivative test. All right, so let's find our critical points from f prime. We go through power rule. Oh, there's a typo there. It should be a minus 20x instead of a plus. So that makes it hard to factor there. So derivative should be 6x squared minus 2x minus 20. Okay, we factor 2 out. Continue factoring. We can also solve for x. Oh wait, messed up. There, should be. Negative 6 plus 5. Okay, we have our factored form. We can solve for x. Okay, so we've gotten this far. I want us to make sure that we understand what we're looking at here. These are candidates for max and mins. These are places locations where we have slope zeros. So what do we do now? Now we can find the second derivative, right? So we're not using a sign line. We're going to take this and we're going to dump it into the second derivative function. So f double prime right? First derivative to second derivative, we just go through power rule. All right, careful with our next step, right? We're not going to set this equal to 0. If we set this equal to 0, then we're looking for something else. Then we're looking for points of inflection. But we're going to take these critical points and we're going to put it in here. Okay, so f double prime of negative 5/3. I get negative 20. The number is not that important. What's more important here? The sign, right? This is less than 0. It's negative. So what does that mean? I'm sorry, negative 22. Sorry,
It's concave down.
concave down, yeah. So concave down, if we can verbalize that, we can also create a picture out of it. And the only place with the slope 0 in concave down narrows down to that point. And the only thing we can conclude about that point is there must be a relative max. I see some students in the past, they want to write order pairs as negative 5/3 and negative 22. So what's wrong with including negative 22 as our order pair?
It's not an actual value.
Yeah, it's not an actual location, right? This is not a location on the graph. This is the concavity at that point. So I'm just going to ask you for the x value. Right? But if I were to ask you for the y value, you would have to put that negative 5/3 back into the original, right? Okay. So let me again talk about why there's so many mistakes about making the correct conclusion. It's because of this. It's because of the fact that we see negative and we want to associate negative with minimum, right? But it's actually maximum. But if we can convince ourselves that negative means concave down and concave down looks like this, I think having the picture is going to make it a lot easier for us to conclude that we're dealing with a max and not a min. Okay, we can do the same thing with the other critical point, right? We'll plug 2 into the second derivative function. So I get 22. 22 is greater than 0. The fact that it's positive is what's more important. The 22 is not as important. Positive means concave up. Concave up looks like this. And if we're looking at this picture, we're going to be able to make a much better conclusion, right? There must be a relative minimum here. And just give me the x value. Let's see those two. And again, it's easy to make a mistake here because we want to associate positive with maximum, but positive 22 is going to tell us that we're looking at a minimum. Okay, any questions with the second derivative test? Okay. All right, number 9. What we're going to do with number 9 is we're going to take the information given, we're going to put that information onto a sign line, and then we're going to translate that on, into a picture of our function based off of these descriptions. So the first is just information about the function. These are just points that we can graph. The second, third, and fourth statement are giving us information about f prime, so we're going to create an f prime sign line to create a visual, and then we can translate that onto a graph. And then the last statement gives us information about the second derivative, or a second derivative sign line. So the first statement is easy to interpret. Those are just ordered pairs. We can just put that onto our graph. 0, 0, and 2, 0. We know the graph. This kind of anchors our graph. We know our graph will have to go through those points. Okay. I'm going to read these statements, and we're going to put this onto our slope sign line. Okay. F prime of x is greater than 0 if x is less than 1. F prime of 1 does not exist, and f prime of x is less than 0 if x is greater than 1. So from here, we can gather that there's a critical point that we're talking about. What critical point is 1? Okay, so let's put 1 onto our f prime sign line. Kind of helps anchor our f prime sign line a little bit. All right, so back to the second statement. Let's see if we can reword this so that it becomes more visual. Okay. What's another way of saying f prime is greater than 0?
The slope is positive.
Positive slope. Okay, good. Positive slope. Okay, where do we want positive slope?
After x equals 1.
Um,
After 1.
it says less than 1. Where's that located? So yeah, to the left, right? So we want positive slope to the left of 1, right? So if you can say that, you can translate that onto your slope sign line. Okay. F prime of 1 does not exist. What's another way of saying that?
Undefined.
Undefined what?
Slope.
Okay, so I'm going to put that to the side here. Undefined slope at x equals 1. The reason why I want to put this to the side is because I want to show that this is kind of a vague statement. And because it's a vague statement, you can interpret however way you want it, which means that your graph may look different depending on how you interpret it. So undefined slope, that could mean a sharp turn. Okay. But it could also mean where the graph doesn't even exist there, so my slope is undefined. You can make it. You could create a vertical asymptote valid, but that's a valid conclusion. You could also make it a hole, because whether it's a sharp turn, vertical asymptote, or hole, those are all undefined slope. One, because the point exists, but is continuous, but not differentiable. Here, it's not even continuous, so there's no chance of it being differentiable. So I want to give these options to you, but if this was on the quiz, you can decide which one you want to choose. You don't have to do all three. Okay, you decide. I'll show you what the graph would look like if you're choosing different options, though. But we'll put that off to the side. We'll come back to it. Let's go to the next statement. F prime of x is less than 0 if x is greater than 1. Can you rephrase that? Negative slope after 1. Negative slope to the right of 1. Okay. The picture is becoming clearer. Having these arrows is going to be helpful when we sketch our graph, right? Okay, we have one more statement, which is going to give us information about curvature. F double prime is greater than 0, x is less than 1. Can you say this a different way? What's another way of saying f double prime is greater than 0?
So concave up.
Concave up. Okay, where do we want concave up?
When it's not equal to 1.
Okay, what is not equal to 1? So basically everywhere except 1. So 1 is also a critical point because it's going to help separate our intervals, right? So to the left is concave up, to the right is concave up. There's no concave down. The only place where it has neither concavity is at 1. So we want concave up here, concave up here. Okay, look at these statements. Look at what we created. Any questions? So we have our slope behavior. We know what our curvature is going to look like. So I'm going to create a graph. I'm going to use a sharp turn here. I'll show you what a vertical asymptote and holes could look like, but I'll do this one first. So I'm going to have my graph increasing to 1 and then decreasing while maintaining concave up the whole way. And what can we make 1 if I want a sharp turn? It can just be a,
It's the sharp turn.
okay. But it's a relative what? Yeah, relative max. Like, so maybe your graph could look like this. I'm going to just do a dotted line to kind of help show that this is the path I wanted to take. I want it to increase, I want it to decrease. But now I'm going to give it a little bit more definition. I want the graph to be concave up. So I want my graph to have this curve, but I also want the graph to have this curve to the right. So this graph is always going to be decreasing, but it's going to maintain that curve, right? That curvature. It's never going to come up, but it's always going to maintain that curve all the way through. Okay. Any question with this interpretation? Okay. Now, if I want to do a vertical asymptote, I could create a graph with that feature as well. Increase, concave up, decrease, concave up. This will work as well. Either one. Or if I want to do a hole, I could put a hole here. That could work too. Okay, any questions with number 9? Yes.
Why did you say there was no concave for that?
Okay, the reason why is because of the statement. It says f double prime is greater than 0. This means that it's everywhere except 1. So that means I want concave up to the left of 1, and I also want concave up to the right of 1. 1 just helps separate my 2 intervals. Yeah. Good. Any other questions? So talking about pairing, slope, and concavity, I do want to spend just a minute to make sure that we understand what the pairing looks like if I match a specific slope with a specific sign of concavity. So if you guys just can find space on any sheet. So I want to just draw this diagram, make sure that we understand the different types of curvature that we can experience in the graph. So I'm going to just create a diagram here. So our graph can have this feature, right? It could look like this. It could look like this. This. Or this. So imagine taking a circle and just breaking it up into 4 parts. So I'm going to ask you, what is the slope and concavity for each of these curves here? So what do we have here? Slope is positive, concave, down. Okay, so that means dy dx is greater than 0, right? First derivative is positive, but the second derivative is negative. So when you have positive f prime and a negative second derivative, this is what the graph will look like. It'll maintain that curvature, that shape. Okay. What about this one here? Slope? Negative. Concave? Down. So both negative, right? So I can say dy dx is less than 0. d2y over dx2, that's just notation for second derivative, is also negative. Negative slope, concave down. That's what that curvature looks like. Okay, how about this one here? Slope. Yes, slope negative. Yeah, negative slope. Concave. Right, this is concave up, right? It's decreasing, but it's concave up because it kind of has that, resembles that parabola opening up shape, right? So we say dy dx is negative, but d2y over dx2, second derivative, concave up, so positive concavity. Okay, how about this last one here? Slope. Positive slope, concave up, okay. So both positive. So as long as we're dealing with a smooth curve, all of our graphs are going to have, it's going to be a variation of one of those four shapes, right? All right, let's see if we can get through number 1 on worksheet 2. We're not going to get very far into it, but I will finish the rest of worksheet 2 this afternoon in the help session. So I know many of you guys didn't get a chance to print it out, but you can just copy this down. This is our function. G of x is equal to 16 root x minus x squared. So it says g of x, we have our function. We just want to find the critical value. So can you talk me through what steps we take for finding critical values? We go ahead and we find what? Derivative and set equal to 0. The thing that's a little bit more involved about this problem is that there's going to be a denominator portion that's going to come out of it, and it's not going to be a clean fraction, so we got to push it, create a fraction out of it, because there's 2 locations that we may have to look for critical points, right? We have to search for it in the numerator, and also we have to look for it in the denominator. Okay, so spend a minute, see if we can get that set up, find the derivative, and see where that denominator could show up, and we may need to do a little bit of finding common denominators here. Yeah. Mm-hmm. I got it ready for power rule. Now I can bring down that 1/2, right? Okay, any questions so far? Good. We see where our potential issue is going to be, right? That negative 1/2 is going to cause some denominator issue. And the 8 is going to stay up, right? It's just the x that's going to come down. But all of a sudden, we see something that is not quite clean we would like this to be one fraction. So now if I can find a common denominator, I can balance my numerator, and then I can merge it to be one fraction. And that's a much better place for us to look for critical points. Right now, then we'll have two clear locations to look for critical points. Okay, how do I balance these fractions here? What's my common denominator?
X.
X to 1/2. So I'm going to just write this out twice because that's ultimately what we want from both our fractions. First fraction, my denominator does not change, so my numerator is not going to change either. But the second fraction, my denominator is definitely changing. So how do I balance my numerator because of this?
Multiply 2 by x to the 1/2.
Okay, so it's going to be 2x times x to the 1/2. If I'm multiplying x's, I'm going to be adding exponents, right? So 1 plus 1/2 is 3/2. Okay, so now we're in a much better position because our fractions, our denominators match. We can now have it as one fraction. We can look for critical points in both locations now.
Mr. Yang, would it be an inequality instead of an x equal because any value to the less than 0 would make it undefined?
Yeah, you're right. If we come across negative numbers, it would not fit because it's not part of our domain. But I'm not going to have that as, you won't have that issue on the quiz where you have to decide whether to keep the critical point if I just ask you for critical values. But you're right, yeah. Obviously there's a domain and that domain needs to be met. Okay, are we good up to this point? So now we have a nice clean fraction. We have two places to look for critical points. Set the numerator equal to 0, set the denominator equal to 0. Okay, and whatever we receive will be our critical points. Divide both sides by 2, I get 4. I want to get x by itself. I want to undo that 3/2. So if I raise both sides to the 2/3, I can solve for x. So you can either tell me x is 4 to the 2/3, or you can square the 4 and make it cube root. Okay, either is fine. Okay, what's my other critical point? Just 0, yeah. So 0 makes the slope undefined, but it's still a critical point. It's still a value that is valid for our function. Okay. So you have two critical points, and that's it. Okay, any questions? Okay, the rest of this worksheet I will spend time going over in the help session. And then tomorrow I will answer questions that you have about 2. So if you don't have any, we will continue to worksheet 3 and just get some more additional practice. Okay, quiz Thursday. Open notes, bring your calculator.
I'm gonna go get my photo taken because I have to go get it during study hall. Is that okay? Thank you. I don't have a lit class here, so they just told me to go.
Wilson, right?
Yeah.
Okay.
Thank you.
Mhm.
Just tell her.
All right, that's all I have for you guys. Have a great day.
Thank you.
Bye.